Yeah. Expectation V for nth stationary state. What you got? Can I write it as half of En or half of En plus half h bar omega, isn't it? So similarly, you can show that expectation T, kinetic energy, for nth stationary state, that's equal to half of En. Or I can write like this: what is expectation of Hamiltonian in nth stationary state? Yeah, so just do that one. Psi n star h cap psi n dx. H cap into psi n is equal to En into psi n. Am I right? Psi n star into psi n dx. What is this one? This is normalized. That's equal to En. Am I right? Now expectation h cap. So h cap you can write as t cap plus v cap. Am I right? Since these are additive, you can write expectation h cap, because expectation is a integration. Am I right? Integration of two addition of quantity is equal to integration of individual, and you can add them, isn't it? That's why you can just write it as that's equal to expectation of t cap plus expectation of v cap. What is this one in case of nth stationary state? What is this one? En. What is this one? En by 2. What is this one? Isn't it? You don't have to even solve. If you solve one of them, other one you can get it like this. This is the idea. Expectation h cap can be written as expectation, because Hamiltonian is equal to kinetic energy plus potential energy. Is it okay? So now one thing you should remember here is half of En plus half h bar omega. Expectation of kinetic energy is equal to expectation of potential energy. That's equal to half of total energy. Expectation of potential energy is equal to expectation of kinetic energy. That's equal to half of total energy. This is what you better remember. If you remember this point, if you need expectation x square, okay? If you need expectation x square, you can go for this one. What is V? Yeah. What is that? Both are equal to half of total energy. En is equal to n plus half h bar omega. That's what I have written. Is that okay? Yeah. Now, if you want expectation x cap square, you can go for this one. What is expectation V? Half m omega square x square. You can balance that half m omega square constant right hand side, and you can find expectation x square. If you need a expectation p cap square, in case of nth stationary state, you can go for this one, because expectation t contains expectation p cap square, isn't it? If you remember these two for the nth stationary state, you can find these two quickly. You don't need to remember wave function at all. And even if I draw the wave functions, look at here, again, it's our habit. As I told, we first draw what you call potential, then on that potential we draw wave function, energy and all, okay? Half m omega square x square, okay? Your ground state is actually symmetric. That's Gaussian. Psi naught. This is psi naught of x. So your first excited state is like this actually. So your third state should be like this. Symmetric again. It will not be 0 quickly here. It will go to 0 slowly. Is that okay? Psi naught, psi 1, psi 2. You know what is psi naught, you know what is psi 1, isn't it? Psi naught is Gaussian, psi 1 is x into Gaussian, that kind of function, isn't it? Now look at here, if you take mod square of this, I can just draw them. Mod psi naught square again Gaussian, mod square is Gaussian only. If I just draw them, mod psi naught square, it will be like this only. Mod psi 1 square, it is I think it's not getting to 0, it will go to 0 slowly. Is that okay? So similarly, mod psi 2 square, what is that one? Mod psi 2 square, it is these peaks are of not same height, okay? These two are of same height, this is little lower. We shall see that one, what are the significance of this and all, okay? As a function of x. Now look at all distribution. Again, mod square, we call it as distribution, am I right? It will decide probability, amplitude and all. Now if you do the position measurement here, what is the expectation value of x you can predict? You are doing the position measurement here, here or here in any nth state. Expectation x. What is expectation value of x? These are symmetric about x equal to 0, isn't it? What are the expectation value of x? If you take identically prepared system, if you do measurement on millions of those systems, what would you get? Expectation value. Speak up. Yeah, so can you hear me? Yeah, why it is 0? Again, why the peaks are not same? This all are depends on this function, okay? This function is actually, I think, second Hermite polynomial multiplied with Gaussian, okay? So it all decide, again, the function will decide that one. Psi 2, we don't know what is psi 2, we shall see that one later. I'll give the general formula, but it all depends on that particular function actually. Your distribution is symmetric about 0. I think this is the fifth time that I'm saying. If you do the measurement, you will get as many reading in the positive x-axis as that of negative x-axis. If you take average, you will get 0. Your distributions are symmetric, whatever the distribution you take. So that's why you can write for nth stationary state expectation x cap is equal to 0. That is one idea. If you know that all distribution mod square, again, even though it is even odd, when you take mod square, all of them are even, isn't it? All of them are symmetric about 0. So that's why expectation x cap for nth stationary state, it is 0. Okay, I'm talking about stationary state. Okay, I'm talking about stationary state here. Now look at here. You can find it in other way also. Minus infinity to plus infinity, x into mod psi n square dx. You can write like this. Now look at here. Your limit is symmetric here. Minus infinity to plus infinity, and x multiplied with mod psi n square. Whatever psi n here is, mod psi n square is always even function. If you replace x to x by minus x, suppose if you had psi 1, psi 1 star into psi 1. Psi 1 is odd function, but odd function multiplied twice. That will become even function. That's why mod psi n square is always even. Whatever, whether psi n is even or odd, mod psi n square is even. Even function multiplied with odd function. Total is odd function. This integral vanishes. You can think like that also. So that's why, so somehow you can look at here, you can just write for stationary state, expectation value of x cap for nth stationary state, that's equal to 0. So you can use time dependent wave function also. Again, our result is not different, isn't it? Why? That exponential time factor, that will cancel up actually. Okay, so that's why you can use m into d expectation x by dt as expectation p, isn't it? That's also equal to 0. That's what we have seen for any stationary state, expectation p equal to 0, isn't it? Now our next part is to find expectation x cap square. Actually, original method is yesterday I have shown that one. Am I right? You should take x cap operator in terms of a plus a minus. Then you have to sandwich between psi star and psi, and you have to operate. That is the ideal method actually. But we don't have to do that one. We already did that one for expectation v. Am I right? For expectation v, we did that procedure, but practice that one. Okay, later it is needed. Suppose if you need expectation x cap cube, again, can you do it as a homework? Find expectation x cap cube for nth stationary state. Find expectation x cap raised to 4 for nth stationary state. These are needed for harmonic oscillator. Can you just tell me what is this one, expectation x cap cube? Go for integral. Expectation x cap cube. 0. Why? Odd function, isn't it? X cap raised to 4, it is not odd function. Even function multiplied with mod psi n square integrated, isn't it? That's quite difficult. That's why you should go for again operator method. You have x cap square operator. Yesterday I did that one. You should find raised to again you should take one more square, and then that is a very lengthy operator. From that operator you should carefully choose some of them which lead to non-zero integral. Carefully and do that one. Try to do. It is there somewhere in perturbation theory. Okay, just try to do that one. Expectation x raised to 4. Remember, you can use expectation p is equal to m into d expectation x by dt if you found this expectation x from time dependent wave function. Are you getting my point? So now look at here. What I do here is, here I'll write it as psi n star x comma t x cap psi n x comma t dx. If I substitute, what will happen here? If I substitute, what will happen here is this is equal to psi n star into e power I e n t by h bar star. Okay. So this is equal to psi n into e power minus I e n t by h bar. These two will give e power 0. Now look at here. But even by taking what you call time dependent wave function, I found that one. I found this one by taking time dependent wave function. Then if a time parameter comes, then it should come here. It is not coming. It is independent of time because it is stationary state, isn't it? We have stated that one, isn't it? If you have taken time dependent wave function, now you can use this one. That's what he mentioned in some problem in the first chapter. You should not use this one. If you were using psi n of x comma 0, not psi n of x comma, for stationary state, again nothing does matter actually. Is that okay? For linear combination state, it does matter. Suppose if you have taken expectation x for some particular time, then time parameter will not come, however, isn't it? Even though it depends on time parameter will not come. Obviously time derivative you will get 0. That's why only when you take time parameter here, you can make use of this one. But it doesn't matter whether you take time dependent wave function or independent wave function in case of stationary state. Both will give the same result. Is that okay? Now one more idea. Again, I haven't taken that one. While taking this one, look at here. What is expectation h cap? I hope root of h bar by 2m omega psi n star a plus a minus psi n dx. Am I right? You can do in this way also. Isn't it? Expectation x cap operator which is sandwiched between psi n star and psi n minus infinity to plus infinity, isn't it? Now if you operate a plus on this one, it will take it to one step higher, psi n plus 1, isn't it? Root n plus 1 into psi n plus 1. That psi n plus 1 state orthogonal to this one, integral vanishes. If you operate a minus 1 psi n, it will take it one step downward. Is that okay? And that state is orthogonal to this state. take the integral, that is 0 again. That's why it is 0. You can think like that also. X cap operator contains a plus cap, a minus cap. If you operate them, it will take it out of normalization. I mean, so orthogonality will come and those integral will vanish. You can think like that also, okay? So because this kind of operator method is needed, okay? I mean, you should know that one, how to apply them and all. Yeah, it is equal to 0. Now x cap square, that's equal. How do you find this one? Now while finding this one, again you should take x cap operator, you should take square, and we did that one. What you can remember to find expectation x cap square and expectation p cap square for nth stationary state, you better to remember this one. Expectation v is equal to expectation t for nth stationary state is equal to half of en, half of n plus half h bar omega. That means expectation v for nth stationary state, that's equal to half of n plus half h bar omega. What is expectation v? Half m omega square x square for half n plus half h bar omega. Now look at, you can take this half m omega square outside. Why? Expectation value is an integral, isn't it? In the integral you can take that constant outside. So that's why you can take this constant this side and you can solve it for expectation x cap square, isn't it? Expectation x cap square for nth stationary state, half got cancelled, 1 by m omega square, 1 by m omega square en plus half h bar omega. That is equal to h bar by em omega, am I right? En plus half h bar by em omega en plus half. Just check it out. Yeah, that's correct. Is that okay? That's correct. Now similarly, if you go again, if you need expectation p cap square, again, even operator method is quite lengthy, am I right? You should take p cap operator in terms of a plus and a minus. You should take square and then you should take expectation. That's also quite lengthy. Again, go for this one. How do you find this one? Take expectation t cap for n stationary state, that's equal to half of n plus half h bar omega. That's why I told you to remember this one. Remember this one. Remember this whole story. What is that one? Expectation T is equal to expectation V is equal to half of total energy. So now this is equal to P cap square by 2m, half n plus half h bar omega. I think 1 by 2 got cancelled here. That's why P cap square is equal to m into m h bar omega n plus half. Isn't it? Just check it out. M h bar omega n plus half. That's correct. Is that okay? Now look at here. Next idea is I think I'm solving one of the problem. 2.11. He asked you to do it for ground state and first excited state by taking wave function. This is for n state. You can put n value equal to 0 to get ground state value. You can put n equal to 1 for first excited state value. Any of these parameters, isn't it? I'm doing 2.12 actually, completely, okay? So now let me find sigma x here. What is this one? Is that okay? So this is equal to 0. So that's why this is equal to under root of this one. Am I right? X cap square. What is this one? H bar by m omega into n plus half. Similarly, sigma p or sigma px, whatever, root of expectation p cap square minus expectation p cap the whole square. Again, expectation p cap is 0 again for n stationary state. Okay, I'm finding uncertainty in case of n stationary state. That is under root of this one, m h bar omega n plus half. Okay, now multiply them. Uncertainty product, can I call it like that? Sigma x into sigma px. Sigma x, sigma px. Uncertainty product, I am finding that one, and later we shall check whether it is greater than h bar by 2 or not. That's equal to h bar square, m omega will get cancelled, n plus half the whole square. Under root again. You will get h bar into n plus half. Always greater than h bar by 2. Because if n equal to 0, now again take this one. Take n is equal to 0. Ground state, am I right? Psi naught is equal to m omega by pi h bar raised to 1 by 4 e power minus m omega by 2 h bar x square. Okay. So your uncertainty product in case of ground state, that's equal to h bar by 2. I think we did this problem somewhere in the first chapter. In case of Gaussian distribution, if you find uncertainty product, you will get exactly equal to h bar by 2. This is the lowest possibility, isn't it? So this product should be greater or equal to h bar by 2. That is our uncertainty principle. And you will get minimum uncertainty in case of ground state, Gaussian state. Is that okay? No. Again, this formula is for harmonic oscillator. Whatever we are doing, expectation V is equal to half of total energy. That is for harmonic oscillator. This will not work for particle in a box. In particle in a box, what is expectation V? That is 0, because your potential energy is 0 in your region of frequency. Is that okay? What is expectation T in case of particle in a box? That's equal to En for n stationary state. Why? So T cap is nothing but h cap. Particle in a box is different. Is that okay? Don't apply this one for other problem. This is for harmonic oscillator. Is that okay? Be careful. Yeah, you can apply virial theorem for other cases, but not for the problem like particle in a box and all. We shall see that one. Okay, for virial theorem, potential should be proportional to some x power n and all. Okay, mod x power n, like that. Okay, we shall see that one. It is there. Virial theorem is there. We shall study that one. That's a good idea. Any question here quickly? Over? I hope we can do all of this within no time, because all our tricks are involved here. And even if you forgot anything, you can just remember a plus and a minus ladder operator and you can get it done. Okay. Now let me quickly do one more problem. How to apply this ladder operator thing for linear combination state? Let me take that one, 2.13. And later you should solve some TIFR problem on this one. Okay. So there are many problems on TIFR exam. X comma 0, that's equal to a into 3 psi naught of x plus 4 psi 1 of x. What is the first step? First step is to normalize. Okay, you can normalize at time t equal to 0 and you don't have to worry for later time. Why? That's our theorem, we proved. Am I right? If you normalize at any time, it will be stay normalized for later time. Isn't it? So that's why again C1, C2. Am I right? What is mod C1 square plus mod C2 square? Mod a square into 3 square plus mod a square into 4 square should be equal to 1. Am I right? Mod a square into 25, 3 square plus 4 square, a equal to 1 by 5. Isn't it? Now I got that one. Let me quickly write 1 by 5 or 3 by 5, 4 by 5. Can I write like this? Normalized part is 3 by 5. This is problem number 2.13. 3 by 5 psi naught plus 4 by 5 psi 1. Is that okay? Just check it out. So in Dirac notation, they may write 3 by 5 state 0 plus 4 by 5 state 1. They write like this in case of Dirac notation. Okay, if any problem you found with Dirac notation, in place of this ket vector, just use your psi notation and proceed. Suppose now you are not comfortable with Dirac notation, either if they have given like this, or if they have given 1, 2 like this, in place of this one, just use psi 1, psi 2 and just do as it is. Is that okay? Later you will feel comfortable with Dirac notation because it's very handy. You don't have to do integration actually. Inner product itself means integration. You can just avoid that step. So, but now, right now, since you are not practiced with that one, in place of this kind of ket vector, just use some wave function symbol and proceed. So, ket 1 means state 1. He is talking about n equal to 1 usually. Don't write psi, write it as psi 1. Okay, so that psi 1 represents this state. Similarly, ket 2, so write as psi 2 and just proceed with your logic. Is that okay? Whatever you have learned. Okay. Again, if you left with any Dirac notation question, do it like this. State 0 means psi naught. Okay. I think I haven't given harmonic oscillator question, but in case of particle in a box question, is that okay? They have given many questions with Dirac notation. Don't worry. In place of that one, so write representative psi. Representative means it should depend on n also. Is that okay? Yeah. Then proceed. Now let me just do with the wave function concept. Okay, not in any Dirac notation. Now here again you can find mod expectation psi of x comma t by plugging in energy factor. Am I right? 3 by 5 psi naught into e power minus I e naught t by h bar. Am I right? What is e naught? Half h bar omega, ground state energy, half h bar omega. Am I right? So half h bar omega. Now h bar got cancelled. This is equal to half omega t. E power minus I half omega t plus 4 by 5. What is psi 1? Psi 1 is 3 by 2 h bar omega. Am I right? I mean, the energy corresponds to that one is 3 by 2 h bar omega. Psi 1 into e power minus I 3 by 2 omega t. H bar will get cancelled actually. Now you can find mod psi x comma t the whole square and all, but when it comes to expectation x and expectation p, go for ladder operator. Is that okay? Don't go for any integral because quite lengthy, isn't it, to remember psi naught and psi 1 normalized wave function. Yeah, you remembered psi naught, let me take like that, but psi 1 should be also needed, isn't it, in this whole integration and all. Now expectation x cap, that's equal to, look at here, psi of x comma t, what is this one, x cap psi of x comma t. Am I right? Now doing this one is quite lengthy to write, not at all difficult. Okay, very lengthy to write. You may need little more space in your notebook. That's it. Okay, what is this one? Complex conjugate of this part. Okay, let me write like this: 3 by 5 3 by 5 psi naught star. Let me again, psi naught star equal to psi naught, real wave functions. Am I right? So e power I by 2 I into half omega t plus 4 by 5 psi 1 star e power I 3 by 2 omega t. Am I right? Now what is x cap? Again, I should have kept some space for that one. Am I right? What was that? A root of h bar by 2m omega. In case of x cap operator, a plus cap plus a minus cap operating on rest of the part. Is that okay? What is this one? Psi x comma t. 3 by 5 psi naught e power minus I half omega t plus 4 by 5 psi naught e power minus I 3 by 2 omega t. Just check it out. Now carefully you should observe what are the integrals which are non-zero, what are the integrals which are zero. You don't have to worry about time part because you are not integrating with respect to time. You can think of the time part later. But think about space part. I mean psi naught, psi 1, isn't it? If psi naught, psi 1, if it is integrated, that is 0. Why? Orthogonality. Like that, okay? Now, observe carefully. When you operate a plus on psi naught, what will happen? You will get psi 1 state. Root 1 into psi 1. Am I right? You should remember this one. A plus cap operating on psi n is equal to root of n plus 1 state n plus 1. A minus operating on psi n is equal to root n into psi n minus 1. Am I right? But remember, A minus operating on psi naught. What is this one? Yeah, what is this one? Root 0 psi minus 1. Is there any state like that? No. Why? This is 0. We have taken this one equal to 0. Am I right? That is the lowest state. If you operate again lowering operator, you should get 0. Be careful. Don't write psi minus 1. That kind of state doesn't exist. Is that okay? If that state exists, that would correspond to energy half h bar omega minus h bar omega. What is the energy? Minus half h bar omega. Negative energy is not possible here. Is that okay? Negative energy is not possible. Now look at here. When you see the whole thing, A plus operating on psi naught, yeah, you will get psi 1, state psi 1, isn't it? State psi 1, you will have non-zero inner product with this one or non-zero integral with this one. But if you operate A plus on this, again, I have written psi 1 should be there. Psi 1 here. Is that okay? If you operate A plus on this psi 1, it will take you to psi 2 state. If it takes it to psi 2 state, look at here, any integral which is non-zero, psi 2 multiplied with psi 1 integrated, that's 0. Psi 2 multiplied with psi 0 integrated, that's also 0. Isn't it? Why? Psi 2 is orthogonal to both psi 0 and psi 1. Ultimately, you have to multiply and then you have to integrate in the next step, isn't it? Try to do this step with a little more elaboration. I'm doing it directly, okay? So that's why when you operate A plus, only when A plus operated on this one, that part is needed. That part is needed to work out. And in that part also, look at here, that you will get psi 1, state psi 1. That state psi 1 will have non-zero inner product with this one only. Again, if this state psi 1, it has a 0 inner product with this one or 0 integration with this one. Is that okay? I can write this one, root of h bar by 2m omega. I'm collecting non-zero integrals here, okay? In the whole story, I'm collecting non-zero part. What will happen is 4 by 5 psi 1 star e power I 3 by 2 omega t. Psi 1, here also psi 1 comes when you operate A plus. What is this one? 3 by 5 root 1 into psi 1 actually. Root 1 into psi 1, root 1 equal to 1 itself. Psi 1 e power minus I half omega t. This is one non-zero integral. Now look at here, you can take this time part outside. The later part of the integration is psi 1 star into psi 1. That is again you can explore normalization. Isn't it? You don't have to do any integration at all. In Dirac notation, this is still easy. We shall see that one later, okay? After third chapter. This problem will be still easy if you handle it with the Dirac notation, okay? Now plus A again. Now A plus operated on this one, it will take it to other state and no other integral will be non-zero, okay? I have taken A plus operated on this one. Which of the integral is non-zero, okay? If you operate A minus on this one, what will you get? 0. You don't have to worry about that one. But if you operate A minus on psi 1, you will get psi 0. That psi 0 have got non-zero integral with this psi 0. 0 integral with psi 1. Is that okay? So that's why that is psi 0. Root 1 into psi 0. Root 1 into psi 0. Okay? Root n into state n minus 1. Root 1 into psi 0. Okay? So that's why again when you operate this one, other integral is this will become psi 0. This will have non-zero inner product with this one, that is 3 by 5 psi 0 e power I 1 by 2 omega t, isn't it? 1 by 2 omega t into 4 by 5 psi 1 e power minus I 3 by 2 omega t. Sorry, dx, just check it out. Now here also again, wait a second. A minus operated on this one, you will get psi naught, root 1 into psi naught. Now here also you don't have to do integration. Again, if you take time part and this constant multiplication outside, what will you get? You will get again integration, which is normalization integral, again equal to 1. So can I write last step directly? Root of h bar by 2m omega, okay, 4 by 5 into 3 by 5. What is 4 into 3? 12 by 5. So sorry, 12 by 25. Here also 12 by 25, it is outside. Now in this one, if you take this exponential part outside, what you will get? You will get integration of mod psi 1 square, which is equal to 1. That's why I'll take care of only about exponential part. E power 3 by 2 minus 1 by 2. E power I omega t. E power I omega t. So plus, here again, this multiplication is taken outside. E power minus I omega t. Just check it out. You can write in terms of cos, 2 cos omega t, isn't it? 2 cos omega t. So that this is equal to 24 by 25. 2 I have taken here, root of h bar by 2m omega into cos omega t. No, any mistakes here? No, that's correct. That's correct. Now you have taken time dependent wave function to find expectation x. That's why you can use Ehrenfest theorem for expectation p. Is that okay? And just take a derivative. Am I right? It's a derivative times this one. Now again he is asking measurement problem, part C, D of the question. Okay, if you do the energy, if you do the measurement of energy of the particle, what value you might get? You will get either E0 or E1. What is the probability? Mod square of the coefficient. Those are the respective probability. Is that okay? Again, P cap, look at here, expectation P cap. If you take derivative, you may get minus sine omega t, but sine omega t is always not negative. Are you getting my point? Depending on the time. Again, what he said, again, m into d expectation x by dt, am I right? You may get one more negative sign, but sine theta is also negative for some value of theta, am I right? That negative will get cancelled, okay? It will not be negative always, it depends on time. Expectation P, okay? It all depends on time. Sine theta is not always positive. Even though you get minus sine theta here, where theta equal to omega t, okay? Sine theta may be negative again, so that the whole quantity may be positive, okay? It will be positive for some time, negative for some other time. It all depends on omega t, okay? Yeah. Now, if they ask any energy measurement problem, look at here. If you do the energy measurement, either you will get E0 or you will get E1. I mean, it's just like linear combination of translation state of electron. If you do observation, it will show that either it is passing through slit 1 or it is passing through slit 2. Like that. Is that okay? It's a linear combination of two energy eigenstate. If you do energy measurement, you will get either E1 or either E0 or E1. These are the possible measurement outcome. Remember, if you do measurement, remember again, I think I have given one note on measurement. Isn't it? Just read out that one. So keep reading that one. If you do measurement, outcome is one of the eigenvalue, not average value. Out one is one of the eigenvalue. Just like electrons show off itself in one of the slit. Isn't it? Like that. Now, with what probability? With what probability? Probability of getting E0. What is this one? This coefficient mod square. It doesn't matter whether you have this factor or not. Suppose if you feel this factor is disturbing, take this factor and then take mod square, then again this will not introduce anything, isn't it? Is that okay? Mod square of this one is 1 again. So that's why probability of E0, that's equal to mod square of this one, 9 by 25. Probability of E1, that's equal to 16 by 25. Obviously if you add you will get 1. Either you should get E0 or you should get E1, either head or tail. There it is equal probability, here it is this kind of probability. Coefficient will decide probability amplitude. Is that okay? Any question quickly? No, expectation P is negative because of cos omega t differentiation, okay? What I am saying is minus sine omega t, it is not always negative. Minus sine of 3 pi by 2. What is 3 pi by 2? Sine 3 pi by 2 minus 1. Am I right? It is positive. Whole quantity is positive. Is that okay? It all depends on it. Yeah, let me think of that one, okay? No, why can't expectation value be negative? Expectation value of momentum, am I right? If a particle is moving in the positive x direction, suppose if you do momentum measurement, if you found particle moving in the positive x direction, you get your momentum positive. Suppose if you do momentum measurement, is that okay? Suppose if you find particle which is moving in the negative x direction, you will find momentum negative. It should be real, okay? It cannot be imaginary, it should be real, but it can be negative also. Is that okay? Expectation value can be negative. Now, what it is saying is expectation P, average of P, if you take one particular time, suppose if you have again identically prepared system, and you are doing the measurement of all system at one particular time, then again finding expectation P, if you substitute some value of sine omega t minus sine omega t naught, if you substitute this t naught, at that particular time you are getting expectation value. That means you should take identically prepared system, you should leave all of the system up to time t naught, and you should do the momentum measurement, and you have to take the average. It all depends on that t naught, okay? We may get average P negative, obviously. You may get negative, okay? Suppose I have potential like this. Okay? So in this potential, again x range is minus infinity to plus infinity. You solved Hamiltonian, I mean you solved h cap psi n is equal to En into psi n, am I right? You solved that equation. I mean solved means you haven't solved differential equation, but we found everything almost, isn't it? Where you got En is equal to n plus half h bar omega, isn't it? And psi n is equal to, actually you got like this, am I right? En into a plus cap operated n times on psi naught, like that. Again, you found somehow everything. Or now let me write psi naught here. What is psi naught? M omega by pi h bar raised to 1 by 4 normalization factor E4 minus m omega by 2 h bar into x square. Now let me take V of x is equal to half m omega square x plus x naught the whole square, or x plus a the whole square, where a is positive. Or let me take it x minus x naught, x minus a the whole square. I have taken a somewhere, yeah, x minus x naught the whole square, okay? Now, which of this result will be affected? You have changed that one, am I right? Can you plot this one? If you plot this one, what would you get? This is perfectly parabolic, am I right? Half m omega square x square. If you plot half m omega square x minus x naught the whole square, suppose x naught is positive, it will be like this. It will be shifted forward. Am I right? Just check it out. Now, what are the quantities? Whatever I have written here, I have written one is energy, other one is wave function. Which of these two will change? Which one will be unchanged? Whether both changes the question. Wave function will change. What about energy? Will energy changes? Energy will be unchanged. Why energy will be unchanged? Why energy will be unchanged? Because I can explore this fact in many other problems, okay? Why energy will be unchanged? Now I told you choice of origin is left to us. God haven't fixed any origin. You have some potential. It's all of our choice where you choose the mean position or where you choose that x equal to 0, isn't it? That's why only change is change of origin here. So change of coordinate here. And choice of coordinate is left to us. Isn't it? Yeah, coordinate will decide wave function. Definitely wave function will change. Here it will be even and odd. Here it will be neither even nor odd, isn't it? You will get that situation. But energy will not change. Energy, which is a physical quantity, it should never depend on choice of coordinate. Is that okay? Energy depends one parameter, that is omega. This omega. What does this half m omega square x square, what does this signifies? This is k, am I right? K in place of k we have written m omega square. That will decide curvature. I told you. What is that k? That is second derivative. That will talk about curvature, how fast the curvature is, how curved it is. So that's why the curvature is a physical quantity, not where this curve located. Is that okay? That's why this potential gives the same energy. En is equal to same. If you take this potential, En is equal to n plus half h bar omega only. Physical interpretation, okay? Not any mathematical. I don't have to solve mathematics again for that one. I can physically interpret like this, okay? Now again, I'll not write psi n. Again, psi n you can find like this, but let me write psi naught of x. Now look at here. It is Gaussian here, am I right? Psi naught of x was Gaussian here. Now obviously, the same Gaussian should be shifted forward. Isn't it? It all depends on potential. Potential will decide everything, isn't it? That's why, what is this one? In this case, that's equal to, in this case, m omega by pi h bar raised to 1 by 4. That this normalization factor, it depends on area under the curve. Area under the curve will not change if you shift the curve. I think I have shown this one in the first chapter. Not in this case, but in case of Gaussian function. Is that okay? And that is into e power minus m omega by 2 h bar x minus x naught the whole square, but this will become neither even nor odd. Is that okay? Neither even nor odd. I have written ground state only. I am not discussing higher states, but ground state looks like this. It's a Gaussian, shifted Gaussian. Take a note on this one. I have a note on this one. Just think over it later, okay? Energy depends on omega. How this omega comes, again, how this omega related to potential omega, again it is related to k. K is nothing but second derivative. Second derivative is nothing but how first derivative changes, how your slope changes, how fast your slope changes. If you change the curvature, omega will change, k will change, omega will change. Is that okay? If you change the shape of this curve, then obviously your energy will change. It has nothing to do with choice of the origin. Whether you choose it here or you shift it here, it doesn't matter. Yeah, it is even with respect to x naught. Okay. Now look at here. In this case, in this kind of situation, what is average x naught? So what is average x here? Now see the distribution. Mod psi square will also be like this, isn't it? What is average x in this case? How it is 0? What is average x? We should do position measurement. Am I right? I told you this is nothing but a kind of histogram. If you take average again, it is symmetric about x naught. It will average out to x naught again. Is that okay? Be careful. Be careful. Again, you better to go back to first chapter and read out whatever I have interpreted. Is that okay? Yeah. Now what I do here is, I'll take one more idea, okay? Now I have one Hamiltonian. I'm adding one constant V0 to this one. I'm adding one constant V0 to Hamiltonian. Now what is the result? Let me take it like this, okay? H of psi n is equal to En into psi n. Is that okay? We solved the time independent Schrodinger equation. H cap psi n is equal to En into psi n. Now what I do is, I'm going to again actually that was the best idea. I added H0 to V0. I'll call it as some H cap new, no, H n should not be used, H cap total. Remember, adding potential means adding V0, which is a constant, okay? I'm adding a constant to Hamiltonian. Or you can say adding a constant to potential also. Is that okay? If I'm going to add a constant to potential, is that okay? I'm going to add a constant to Hamiltonian. I can say like that, isn't it? Now adding this one, that means you are adding that one throughout your region of interest. Adding V0 throughout your region of interest, I mean minus infinity to plus infinity. You are adding one constant value to Hamiltonian. Now, so when you go back, if you check out the, what you call, again you already solved, okay? This is solved, this equation is solved. Now what is the energy of this total Hamiltonian after adding a constant to earlier Hamiltonian? Now H cap T, so if you operate on psi n, you will get Et into psi n. We shall check it out. What is this psi n? H cap T, H cap plus V0 psi n is equal to Et into psi n. What is H cap psi n? En into psi n plus V0 into psi n is equal to Et into psi n. En plus V0 into psi n is equal to Et into psi n. What is E total? En plus V0. Isn't it? E total is equal to En plus V0. That's why adding a constant to what you call Hamiltonian, it will lead to adding that constant to total energy. Adding a constant to total energy. I think we had a similar idea somewhere in the earlier chapter, am I right? Somewhere in some problem he mentioned about this one. Just check it out. I think first chapter. Suppose if you add V naught to potential energy constant, again what will happen? Wave function picks up time dependent phase factor e power minus I V naught t by h bar. That's what he commented. Problem number 1.8 from first chapter. Now look at here. If you want to write psi n of x comma t, okay, psi n of x into e power minus I E n t by h bar, am I right? So for this new Hamiltonian, if you want to write psi n of x comma t, am I right? That's equal to psi n of x into what is new energy? E power minus I E n plus V naught t by h bar. You should use new energy in that case, isn't it? Now what is this one? It's equal to psi n of x into e power minus I E n t by h bar e power minus I V naught t by h bar. This is what he commented in that problem. If you add any constant to potential or Hamiltonian, both are same, your wave function will pick up time dependent phase factor, this one. And it will not affect any probability distribution. Why? Mod square, again it will get e power 0. It will not going to play the role. Can you observe this fact? Energy will be changed like this, wave function will be changed like this. I mean, if you know what happens to energy and wave function, you can solve any problem. Is that okay? Now, I'll give you one problem, try to solve that one. Think over it and try to solve it. One homework problem, okay? Example. So what is the energy eigenvalue of this one? V of x is equal to half m omega square x square plus b into x. With all concept and logic, whatever you learned, you can solve this one. This part we already found. What is the energy eigenvalue for this one? Half m omega square x square n plus half h bar omega. What is for this one? Is that okay? What is for this one? Try to find that. Now let me quickly take you through. Yeah, you should make it as perfect square. You should make it as perfect square. X plus something the whole square. You have b into x, am I right? Add and subtract with that one so that you can make it a x plus x naught the whole square or x minus x naught the whole square. Then that is done, because again changing what you call origin, it will not change anything and you can argue something. So try to solve that one, okay? Yeah, that's a good idea. Because the same problem will come in case of perturbation theory, where you don't have to do any perturbation theory. Any perturbation method you can solve like that one. I mean, you don't have to use any what you call perturbation method. You have ideal method. Okay, this is ideal method. Try to do that one. Yeah, we get constant term adding for energy of the harmonic oscillators. That constant term will appear in the total energy. That's what we have shown. Okay, just have a note on last two topic, whatever I have given. One is shifting of the potential. What will happen? Other one is adding a constant to Hamiltonian, what will happen, okay? Yeah. Now our analytic method is solving the differential equation, and he has given that method. Again, I am not going to discuss that one. But in that analytic method, you will get exact function psi n of x. What you got psi n of x in terms of psi naught, isn't it? Not exactly psi n, you don't know what is the exact nature of psi n of x. Now look at here. You have, yeah, can you just give me? While doing that analytic method, you define one parameter called xi, okay? That's equal to root of m omega by h bar into x. That is proportional to x, okay? In place of x, we substitute that one. and at the end, again you get your answer in terms of Hermite polynomial. Psi n of x is equal, again En is equal to n plus half h bar omega. Okay, n equal to 0, 1, 2, 3 and so on. Again same result will come obviously. Okay, we shall discuss one of the problem of again differential equation with variable coefficient. Okay, one problem, it's quite lengthy, so that again we should use power series method to solve that one. Quite lengthy method, is that okay? But we shall do one of them because I want to explain some physical part of that one. Okay, so now if you find psi n of x using that solution of differential equation, you will get this one, m omega by 2 h bar, sorry, pi h bar raised to 1 by 4 into 1 by 2 raised to n into n factorial under root h n of xi. This is not Hamiltonian, okay, this is Hermite polynomial, it is polynomial in xi. Okay, h n of xi into e power minus xi square by 2, where h n of xi are Hermite polynomials. They are alternatively even and odd. Let me just give some Hermite polynomial. h naught of 1, h naught of xi, okay, that's equal to 1. h1 of xi, that's equal to x, sorry, not x, that's equal to xi. Sorry, 2 xi, okay. h2 of xi, that's equal to 4 xi square minus 2. Xi is again in terms of x, okay, you can write in terms of x. That's sufficient, okay, you don't have to by heart now, we shall see that one later. Obviously, if you put n equal to 0, h naught, if you substitute, and you will get ground state wave function, that's it. This is how you should write nth state. Definitely we can't remember all, we use ladder operator to solve any problem. Now he mentioned some what you call in problem number 2.16, he mentioned some properties of Hermite polynomial and all. They are alternatively even and odd. Look at here, even function, constant function is even function, odd function, even function, next one is odd. So again this is always even function, xi square is there, xi square corresponds to x square here. So that's why, since this is alternatively even and odd, this will make the total wave function alternatively even and odd. And that's what I tried to plot earlier. Okay. Now what I do here is, let me just try to plot the wave function. Actually, he has plotted psi 60 mod square. So you have book in your hand. Do you have book in your hand? Because I want to interpret something. So let me plot mod psi naught square, okay? This is the potential. Let me plot mod psi naught square, n equal to 0. Mod psi naught square. Again, this is not sufficient actually. Space is not sufficient. But let me try, okay, anyhow. This is n is equal to 0, n is equal to 1. For n is equal to 1, it will be like this. Is that okay? For n is equal to 2, observe very carefully. I think I have plotted like this only. No. Again, area under the curve should be same, isn't it? You should be careful while drawing this. Area under this one should be equal to area under this one, y should be equal to 1, normalized, isn't it? Be careful. Okay. Now, this would be like that. If you observe, look at here, if you take peaks, just observe for higher state. Wait a second. So like that, he plotted mod psi 60 whole square, isn't it? Mod psi 60 whole square. What he found is, look at here. Again, it's very difficult to draw. What he found is, he found envelope which is this kind of curve actually. Envelope of those peak. Some mod psi 60 whole square. That's what he has plotted, whatever. Have you observed this kind of curve anywhere? This kind of curve? Where you can't differentiate these peaks actually. When you make n very large, it seems like it is almost continuous. Okay? Have you found this kind of curve anywhere in first chapter? What was this one? Rho of x is equal to some 1 by pi root of x square plus x square minus a square curve. X square minus a square or x minus a? X square minus a square. Your classical probability density of harmonic oscillator. Classical probability, is that kind of function? Isn't it? So when you plot that one, do you remember it is like this, where you have minus a here, plus a here. Am I right? Isn't it? Just check it out. Now, in case of classical harmonic oscillator, you got this kind of probability distribution. Distribution is mod square. Is that okay? Again, so this is also a kind of Bohr correspondence principle when you take very high quantum number. For n equal to 0, look at here, for n equal to 0, it is very highly non-classical. Let me tell you why. You got more probability at x equal to 0 where it has a largest velocity. Am I right? It has the largest velocity at x equal to 0, mean position, isn't it? If velocity is higher, probability of getting that one should be lower. That's what we found, isn't it? It is highly non-classical. But when you go for higher quantum number state corresponds to very high quantum number, psi 60, psi 100, psi 200, like that. So some parameter will approach your classical parameter. In this case, that is probability density. Your probability density, so or if you take the peaks, which is envelope, that envelope again, because when you make n very large, you can't differentiate this peak. It seems to be continuous curve. And that will approach your classical probability distribution. That envelope of this peak, that will approach your classical probability distribution. So that's why Bohr correspondence principle says, so for large quantum number, our quantum system behaves like a classical system. For very large quantum number, not even psi 60. In case of psi 60, you can see the peaks. Take psi 1000, like that, okay? So that kind of range. Classical system behaves like, quantum system behaves like a classical system in some parameter. Is that okay? We shall see that one. Similar thing in case of atomic spectrum. So similar thing will happen in case of Bohr atomic model also. Okay, just have a note on this one also. No, now what I am saying is, if there is classical harmonic oscillator, okay, if there is classical harmonic oscillator, suppose these are your extreme positions, so it will move like this. In extreme position, it will go to rest. Am I right? In mean position, this is x equal to 0 is a mean position. In mean position, its velocity is very high. isn't it? In extreme position, its velocity is very low. I mean, probability of getting the particle in extreme position classically should be high. Why? It is moving very slowly. It is spending a lot of time in the extreme position, very less time in the mean position. But quantum mechanically, something different is happening. There is more probability of finding the particle. Again, quantum mechanically, little different is happening. Particle can found outside the classically allowed region also. In case of particle in a box, I should think of that one. Okay, in case of particle in a box, I think how Bohr correspondence principle works, isn't it? I should find. I should find again mod psi 100 whole square in case of particle in a box. Then what you find here is, suppose if it is 0 to A, okay, mod psi 100 means you will have psi 1, I think 99 nodes, 99 zero crossing values actually, okay. So when you plot 0 to A, that's a very good idea, okay. What you will find is, you will find lot of peaks, all with the same height. In case of particle in a box, is that okay? Because that is sine the square, sine 100 pi x by A the whole square. Is that okay? You will get it like this, and envelope will be constant. You have constant probability of finding the particle. Is that okay? Yeah, let me give you some more logic. Okay, while solving the problem, let me give you some more logic. And while solving the problem, I'll tell you to note down something. You better note those down. Okay. Yeah, that's a good idea. Okay, you can interpret that one also. Suppose particle which is free to move 0 to A, there is no probability which is favored. You can't say probability of finding the classically. Suppose it is moving back and forth, and if there is no what you call favoring thing like that, I mean particle is more likely to found here, less likely to found here, then probability density will be constant. Am I right? And that's what you can get here. In case of harmonic oscillator, this was your probability density distribution, and mod psi very large quantum number. When this quantum number is very large, it also tending to same thing. Is that okay? If particle is moving back and forth with one constant what you call velocity speed, suppose, then there is no, again, probability of finding the particle is equal throughout the well, and that will happen when you take it to very large quantum number. Is that okay? Just observe that one. That's a good idea. It's a good question. Yeah, quickly, any more questions? I mean, for very large particle, look at here. Here what I am saying is, even though for a microscopic particle, if you go for very large quantum number, it will behave like a classical. If you take particle size itself is large, definitely quantum mechanical thing will not work. I mean, or you should go for classical. Is that okay? So again, you should take classical interpretation. What I am saying is, take microscopic particle only, these are the quantum descriptions. In case of microscopic particle, go to very higher excited states for very large n, and this mod psi square, it will have distribution which is equivalent to your classical probability distribution. Okay? Again. Yeah, definitely. Linear harmonic oscillator wave functions are different. Look at here. Again, it will not go to 0 suddenly. Okay, it will go to 0 again like this actually. Particle in a box, it is 0 here. Wave function is 0 here and here. Find the difference. Again, you can't say that this particular quantum number will behave classical. You can talk about only approach. You can talk about in the approach of large quantum number, it will behave like classical. You can't say that this particular, from this quantum number, it will start classical behavior. It's not like that. It will approach. It's an approach. Okay. It's a slow variation. Okay.